been discussing the, can you see the screen?
Yes.
Okay. So last time we were talking about the geostrophic and hydrographic balance. What means that there is the, in a horizontal, there is a balance between the X, usually in oceanography and also in meteorology, we define X and Y coordinates where X is west-east and Y is south-north. So we have in the X direction, we have Coriolis force is equal to the pressure gradient force. In Y direction is the same thing, but Coriolis force in the Y direction, pressure gradient force. And then we have in the vertical, the pressure and the gradient force is balanced by the effective gravity. So this is essentially the dynamics of the Coriolis of the geostrophic currents. And so this is in terms of the equation. How do we express this? I already talked to you about, and so that means that as we says that the pressure gradient is uniquely the geostrophic flow, the geostrophic velocity. That means that by determining the pressure gradient, horizontal pressure gradient, we determine also uniquely the geostrophic flow. Let's see, you all know what means the pressure. The pressure means the weight of the water column above the point where you are. Therefore, the higher is the sea level, unless we are not talking of the difference in the density, the higher is the sea level, the higher is the pressure, and vice versa. So if we have the vertically homogeneous water column, so there is no changes of density in the vertical, the current is uniquely determined of the horizontal distribution of the sea surface. Because the sea surface height determines the pressure and determines the horizontal pressure gradient. Therefore, that's as you remember that when we were talking about the satellite, we started measurements in 1992, measuring the sea level, which is one of these images which shows here the sea level in the world ocean. This is essential to determine the geostrophic flow. If the ocean were vertically homogeneous, then this kind of pressure, or this kind of pressure, which is associated to this kind of sea level anomalies, will be equal all over the water column. So what that means? That means that if we have, for example, here is the high sea level and here is the low sea level. So the flow will go this way, will go this direction, leaving high pressure on its right. If the ocean, as I told you, if the ocean were vertically homogeneous, that means that all over the water column, the current will be of the same magnitude and of the same direction from here to there. But the complicated situation is introduced, or the complicated or very interesting situation is introduced by the density, horizontal density distribution. Because if you have a density, for example, here different than density here, then density at the certain depth can completely reverse or change the horizontal pressure gradient, which doesn't have anything to do with what is happening at the sea surface. Therefore, and since the ocean generally is not vertically homogeneous, the density in the ocean changes with depth. That means that that whatever we see at the surface, the sea level distribution, the surface pressure gradient, that doesn't mean that this reflects whatever is happening in the deeper part of the water column. So that's why we say, if we are looking at the altimetric surface height obtained from satellite, that this is the surface geostrophic flow, the surface circulation, which then obviously, in order to get the information on what is happening in a deeper part of the ocean, we have to have the information on the density distribution. Okay. So this is the essentially the flow, the surface circulation obtained from here, and you can see that this high sea level here shows the anticyclonic circulation, the circulation leaving high sea level on its right. And here is the same thing, but the southern hemisphere leaving on its left. So that's the circulation. Then, as I told you before, last time we were talking also about the circumpolar Antarctic current, which is here, which goes all around the Antarctica, and this is the only current. This is the only exchange of water masses between different oceans which happens in all over the world, because this current, as you can see, runs over and connects all the three oceans, and this current is very strong. How do we know very strong that it's very strong? Because the isolines here, you can see the isolines are very, very close to each other. So that means that there is a strong changes of the sea surface with over the unit distance. So that means that the surface pressure, dPdx, for example, or dPdy, in this case is dPdy, is very strong because there are strong changes of the pressure per unit distance. And that's our Antarctic circumpolar current. And let's see what is okay. See, here it is, the Antarctic circumpolar current. On one hand, it can be seen at the sea surface because the surface height is this way here. The surface height is this way. This lower surface height is closer to the Antarctica and higher if you go toward the center. But you can see that if you go to vertical, there is no there are strong changes of density. These are, if you remember, densities are expressed in density anomaly. So that means the density of the water minus 1,000. So that's why we get 27, 27.5, 27.8, and so forth. And here we have 45.8 because we are talking here about the potential density. And so, if the ocean were, if there were no changes in horizontal of the density, if there were no horizontal density gradient, but also at the same time the horizontal pressure gradient, the isopycnus or lines of equal density will be horizontal. But now you can see that in the area where there is a Antarctic circumpolar current, especially, the slope of these isopycnus is rather strong. And at the same place where the slope of sea level is very high. So at this this place, the sea level slope is as very high, is maximum as what it says, what happens in the internal current field or in the internal pressure gradient. And so, as I told you before, so we have the high density here and low density here. So if you do the integral over the entire water column from surface to the bottom, you will get a higher density here than there. So what that means, higher density means that the sea level is lower. The higher is the density, the lower is the sea level. So the sea level will be this way, okay? And the density is higher here than there. So in the surface, since we are at the southern hemisphere, the flow here will be into the slide, into the screen, and the pressure gradient, the internal pressure gradient, that means this one due to the internal density field is acting in the opposite direction. So this is that's what it looks like. And see, sorry, it comes from the screen toward you because we are at the southern hemisphere. And see, this is the sea level. That's the sea level. Sea level is lowest here and going up and up on the open ocean because the density is decreasing. So this is here is at the surface. Here is a low pressure, and here's the high pressure. And at the southern hemisphere, the current, the geostrophic flow is such that it leaves the high pressure on its left. It's opposite to what is happening in the northern hemisphere. And here, due to these horizontal pressure gradients, which are practically compensating, going down to the bottom, the pressure gradient becomes lower and lower, and therefore the current, this Antarctic circumpolar current, is decreasing with depth. It's decreasing with depth not because of the surface pressure gradient, but because of the horizontal pressure gradient due to the density, which acts in the opposite direction with respect to the pressure gradient due to the sea level. So, to observe, therefore, the geostrophic flow, geostrophic circulation, what we need? We need the density, we need the temperature and salinity, and we measure this for the most time. Therefore, apart from measuring the sea level, which is now relatively simple, but it used to be very difficult, it used to be impossible, we have to measure the density or temperature and salinity in order to obtain the vertical distribution of the density and of the pressure. And we in fact want to have a current speed and direction, but we cannot. Here it says, because this is an old, relatively old slide, we can measure the sea level height accurately enough. This will change with improved observing systems, but it's historically the case. This is a slide that has been done obviously at the very beginning of the measurements, satellite measurements of the sea level. Steady state isopycnal slopes tell us that the geostrophic current is varying with depth. This is what we have seen here. What we have seen from the Antarctic circumpolar current, we have the flow at the surface, which is generated by the sea surface height gradient, but then it changes with depth because there are sloped isopycnas in the deeper layer. So there are horizontal pressure gradient due to the horizontal gradient of density. Okay, most currents we see are wind driven and therefore strongest at the sea surface and decaying with depth. Now we have another complication in the system, is in the sense that the currents are not only geostrophic, the current are also generated by the wind. Therefore, we have at least at the moment we do our measurements, we have at least two, from the dynamical point of view, we have at least two types of currents. One is the geostrophic current, which means that this is we will see now in what conditions the geostrophic current, the geostrophic assumption is valid. And most currents are wind driven in the first 1,000 meters, in the first kilometer, and they decay with depth. And then we have also the geostrophic flow, geostrophic currents. And what we measure really is the superposition of these two signals, at least, because we can have also the other time varying currents like tidal currents, and you will see later on what kind of we have a whole spectrum of the variability of the currents in the ocean, which depend obviously on the pattern or on the spectrum of the forces which are generating these currents. For example, this is one example. The other example is the Gulf Stream. Gulf Stream, what has been done in the Gulf Stream as well. In the Gulf Stream, we know that the Gulf Stream passes here. This is the Florida coast, and this is the Gulf of Mexico, and this current goes northward. And if you do the measurements here, perpendicular to the coast, you do the measurements of the density, for example, you obtain the density field. This is the vertical distribution of the density field from the coast. This is the coast to the open sea. This is the Bermuda Island, and what you can see, that's the vertical distribution of the density, and you can see also the similar thing as what we have seen in Antarctica. We have seen that there's this strong horizontal gradient of density in deeper layers, while in the surface layer, the horizontal gradient of density is relatively low. So the density is practically, the isopycnas are practically horizontal. The more you go to the bottom, the more sloped are these isopycnas. So that means the more go toward the deeper layers, the higher is the horizontal pressure, the gradient. Here it is, and these are the currents, because these are the measurements of the current. You can see this very well because there is some problem with this slide. But the current is, as you can see, this is the current which goes into the slide, into the screen, because it has associated to this kind of the horizontal and vertical distribution of density. There is the horizontal and vertical distribution of the sea surface. How? If we have next to the coast, if we have a lower density means that the water column is the volume of the water is larger. The lower is the density. The lower is the density. The lower is the density. The higher is the density. The volume of the water column is stretched. No. It says that. Can you hear me? Okay. So what that means? That means that here, in this part here, since the density, if you do the integral of density from the surface to the bottom, you would get the density much higher here than here. So that means that the sea surface here will be lower will be lower here than here. Okay, so the surface height will be something like that. Okay, so we'll have the higher sea level at the open sea and the lower sea level to the coast. Since we are in the northern hemisphere, the current geostrophic flow will flow northward because it has to leave the high sea level on its right. Okay, this is the surface current. This is the surface current, which has the circle. The larger is the circle, the larger is the current, obviously. When you go deeper and deeper, due to the horizontal pressure gradient, this northward flow becomes weaker and weaker because of the horizontal pressure gradient due to the density distribution, which then weakens and weakens the original horizontal pressure gradient due to the sea level slope. So this is how the both horizontal and vertical flow, geostrophic flow, looks in here it is, this thing. Okay, so that's this thing. How can we schematize this this thing, and what is the phenomena which is, or what is the phenomena associated with this combination of the sea surface and internal density field distribution. Since we are talking about the water column, which is not vertically homogeneous, so there are changes in density from surface to the bottom. We are talking about what we call in oceanography baroclinic motion. Then we have a barotropic motion or barotropic flow, or barotropic fluid, where the density is vertically mixed from the surface to the bottom. But let's look at the simple situation where we have a two water column, HA and HB, where the HB is higher than HA. So it's similar. The situation is is similar as the Gulf Stream. Okay, close to the coast, to the left-hand side, you see the lower water column, the lower sea level, and you have here the higher sea level. And then, obviously, due to this gradient, we have the pressure gradient force is oriented from the higher sea level to the lower sea level, because this is the definition of the pressure gradient force, that the pressure gradient is oriented from the higher pressure to the lower pressure. And so we have a northward flow, surface northward flow, or surface flow into the screen at this depth, at the surface. When we go to the deeper layer, so you can see here, these two here the water column is vertically mixed, has a rho B density and a rho A density. So we only consider the case where there are horizontal density difference. But then there is horizontal density difference, but there is also a horizontal gradient differences due to the different water column, but then also due to the different density. Since the water column here, HB, is higher than HA, means that rho B density of the water column B is lower than the density of the water column A, because here is the lower density, and therefore the water column is higher. So the internal pressure gradient is the pressure gradient which is due to the different density distribution. So we have the horizontal pressure gradient is from A to B, internal, which is opposite to what is external or barotropic pressure gradient, which is from B to A. So since these two pressure gradient forces are all in opposite direction, the deeper we go, the weaker is the sum of these two pressure gradients. And therefore, since we have in equilibrium Coriolis force with the horizontal pressure gradient force, the lower is the horizontal pressure gradient force, the lower is the velocity, the geostrophic velocity. So the geostrophic velocity as a result of this kind of horizontal and vertical distribution, the horizontal, mainly of the horizontal distribution of the density and of the sea level height, the geostrophic flow decreases with depth. You can see it decreases with depth due to the decreasing of the pressure gradient force. But what is what can be the result of this thing? The result of this thing can be that due to this reduction of the geostrophic flow can be or the horizontal pressure gradient, combination of the horizontal pressure gradient of the internal and external pressure gradient could be that at a certain depth the current changes the direction, because the internal pressure gradient becomes higher and stronger than the external pressure gradient. Therefore, we have so further down, as it says here, you can have equal mass and equal pressure, hence no pressure gradient force, since total mass in B and A is the same. So if we made the integral over here from here to there and do the integral over the entire water column, we will get the same mass here as here, because here this density is lower than there. And therefore the pressure gradient at a certain depth goes to zero. What means that the geostrophic flow goes to zero at a certain depth. And obviously going even deeper, the geostrophic flow changes direction. This thing is called the thermal wind relationship. Thermal wind relationship means that explains the vertical shear, the vertical changes of the horizontal geostrophic flow due to the horizontal pressure gradient force, internal pressure gradient force due to the uneven distribution of density. There is a special case in this situation where if HA and HB are equal, okay, yes, let's assume that HA and HB are equal. Rho A and rho B are equal, and HA and HB is the same as it here. In that case, the pressure gradient force would not change at all, because the rho A and rho B being equal, they don't contribute to changes to the pressure gradient force. The only differences in the pressure gradient force between this and that is due to the different height of the water column, since rho A and equal rho B. So this is what is, in that case, whatever we measure at the surface is the current over the entire water column. Therefore, only in the case water column A and water column B between the 2 points, only in that case there will be, only if these rho A and rho B are different, there will be the vertical shear. So in this thing here, we can see qualitatively that the vertical shear, that dVdz, the vertical gradient of the horizontal velocity, is proportional and determined to the horizontal gradient of density. So that's an important relationship which connects the horizontal density gradient with the vertical gradient of the geostrophic flow. Therefore, what that means that if we measure the horizontal distribution of density, if we measure the spatial distribution of density, we would obtain the horizontal gradient of density, and then we would obtain the vertical shear, the vertical distribution of the horizontal velocity. If we have the density, the density varies continuously, so we don't have the two water column different. We have simply the water column A and water column B, and the density changes continuously from in deeper layer. This is again something which is similar to the this is idealized horizontal distribution of the surface sea level and density distribution in the place of the Gulf Stream. Or you can also see this is an example, idealized example of Antarctic circumpolar current, except that it is on the southern hemisphere, so you have to invert the direction of the flow. So what we do is we measure density, which is this red line, okay? The slope down to the right means that flow increases into the page, decreases with depth. We assume or measure that velocity is 0 at depth 3, for example here, and therefore the pressure contours must be flat. These are the pressure contours. These are pressure contours. At the surface, this pressure contour or the pressure line is exactly corresponds to the sea level. If you go deeper, then the horizontal pressure gradient becomes less sloped. And at a certain depth, the pressure contour becomes horizontal, and because this is compensated by the density. So, therefore, here is and below the level 3, which is this thing here, the flow would start going back the other way, out of the page. Therefore, what that means that, in fact, if we look at the Gulf Stream, for example, or even in the Antarctic circumpolar current, the flow in deeper layers is in the opposite direction. So you have a kind of a two-layer structure. You have the surface flowing in one direction and deeper layer in the other direction. Everything is due to the horizontal pressure gradient. Here, see, you can see this. And that's how it looks like in deeper layer. Below the line where the horizontal pressure gradient is 0, there is a flow going in the opposite direction and increasing with depth. Okay? So, what that means? That means that the geostrophic flow we can obtain calculating the pressure gradient force as the difference of pressure between two stations at a given depth. So this flat surface relative to the geoid. Therefore, what we do have to have, first of all, first thing what we have to start with is that we have to know the density field. Once we know density field, then we calculate the pressure gradient force at a given depth, and we go in that way calculating the geostrophic shear. But you have to take into consideration that we are calculating the geostrophic shear. We don't have really the absolute velocity. We don't have because the vertical shear, the vertical gradient of the horizontal velocity is proportional to the horizontal pressure gradient. So that means that you don't have you don't obtain the absolute value of the geostrophic flow. And so, in a certain way, some way, you have to obtain at a single depth, at one single depth, you have to obtain the absolute velocity, and then add to this the vertical shear, and obtain the full distribution of the velocity with depth, in absolute terms. Otherwise, you obtain only a velocity in relative terms. So you have to know at a certain depth, you have to know the known velocity, which is what we call the reference velocity. And then we know how the velocity changes with depth, and from that we compute the velocity at each depth. So how you obtain the absolute velocity, or you measure it at a certain depth, you put your instrument, you measure your velocity, and then doing these calculations of the vertical shear, you reconstruct the velocity all over the water column. Always talking about the geostrophic flow. Or there are some in a historical geography, there was some approach where they say, okay, let's assume that very likely at a certain depth the velocity is zero. This is the zero level velocity, velocity of zero level. Zero velocity level. And then from there they only get the guessed vertical velocity distribution. Okay, so this is what we have talked about. So here is the old-fashioned velocity, old-fashioned approach, where we assume zero velocity at some great depth, what is usually called the level of no motion. And then we compute velocity at all shallower depth. This is useful if you are focused on very energetic upper ocean flow, but not useful if you want to look at small depth deep flows. Small deep flows, you have to also take into consideration that these small deep flows are very weak. Obviously, the better guess or the better assumption is to observe or determine through external means, use of tracers, mass balance, a good guess of the velocity at some depth, what I call the level of known motion, no more known motion. This is essential if you want to study deep circulation. So you can also measure it. But we are now mainly talking about the, let's see, let me just change let me change the PowerPoint, and let's look at this thing here. We have the geostrophic flow, but we are always talking about the geostrophic flow, and but we don't know really. We know that the geostrophic assumption is this is only assumption. It's not this real full equations of motion solution. It's the assumption. So we take certain number of assumptions, and from that we obtain the solution. Therefore, for example, for the geostrophic flow, we neglect the time dependence because there is no d zeta dt, du dt or dv dt. We neglect the horizontal advection. We neglect external forces except the pressure gravity. We neglect the wind influence. Therefore, we have and we assume the hydrostatic equilibrium, which is also the very, very important assumption, a very heavy-duty assumption. Therefore, we have assumed a whole series of things which certainly limit the validity, the value of this geostrophic assumption. So let's see under which conditions or which kind of time and space scale are described. The flow of a time scale and space scale are described, or are very good approximation of the geostrophic flow. So the geostrophic flow, how do we get that? We do what we call the dimensional analysis of the equations of motion. How do we do that? We assume typical values for our ocean, and then see what are the of the velocity of the equations of motion. So what we do, we assume, for example, that the horizontal scale is 10 to the 6 meters, so it's 1,000 kilometers. We assume that the depth is 10 to the 3 meters, so we're order 1,000 meters. These are the typical values, typical values of the geometrical values in the ocean. We assume that Coriolis parameter is 10 to the minus 4, 6 seconds to the minus 1. The density is 10 to the 3 kilogram per meter cubic per second. The velocity is 10 to the minus 1 meter per second, so this is 10 centimeters. We have a two layers. One is 10 to the 3, the other one is 10 to the 1. We have the gravity acceleration, which is 10 meters per second square. So these are the typical values with which we go into the equations and find out what are the order of magnitude of different terms of the equations. So from these variables, what we have assumed up in the upper, we obviously we did pick up this by chance, these typical values. We know that the ocean horizontal scale of the oceans is on the order of 1,000 kilometers, because for example, the Atlantic has a 4,000 kilometer wide. We know that the depth is 10 to the 3 meters, so it's 1,000 meters, which is a very good guess, and so forth. And so if we put these typical values in the vertical velocity, in order to obtain the vertical velocity from the continuity equation, we obtain that the vertical velocity is 10 to the minus 4. So the vertical velocity in the ocean is 10 to the minus 4 meter per second. So 10 to the minus 4 is 10 to the minus 2 centimeters, or 10 to the minus 1 millimeter per second. It's a very, very small velocity if you consider that the horizontal velocities are typical, are on the order of 10 meter per or 10 to the minus 1 meter per second. We obtain then the typical value of the pressure. We obtain the t, the time. The time scale is 10 to the 7 seconds. So we have obtained the typical time scale, which later on you will see, which later on will give us what are the order of magnitudes of the terms in the equation of motion. And so, in fact, if we enter with these 10 to the 7 seconds, the time scale, and if we go and calculate the momentum equation for the vertical velocity, what you obtain that practically dw dt, so that means the time dependence of the vertical velocity is 10 to the minus 11. The advection terms, which is u dw dx and u v dw epsilon and v w dw dz, dz, are 10 to the minus 11, all of them. This is equal, this has to be equal to the to the gravity force. We have the 10 to the minus 5 is the Coriolis force, and we have a 10 is the pressure gradient, vertical pressure gradient force. And what we obtained really that all these terms here, all of them are 10 to the minus 11 except the horizontal, the vertical, the vertical gradient of the vertical pressure gradient and the geostrophic and the gravity force. Therefore, in the vertical, we have this equation. This equation is practically reduced from all these terms here, which we eliminate, and which is correct to the 10 to the minus 6. So the approximation for the hydrostatic equation is 10 to the minus 6. The momentum equation for horizontal velocity in the x direction. So in the vertical, let's summarize so far. In the vertical, the approximation of the hydrostatic equation is extremely good approximation up to the 10 to the minus 6. For the horizontal velocity, in the x direction, for example, but this would be the same thing as in the y direction, du dt, we have u is 10 to the minus 1 meter per second. T is 10 to the 7. So we have a 10 to the minus 8 is du dt. Okay. U du dx is 10 to the minus 8, which is one of the terms of the horizontal advection. And the second term of the horizontal advection is 10 to the minus 8. And the third is of the same order of magnitude. So all these terms, the time dependence, the horizontal acceleration, and the advection terms are on the order of 10 to the minus 8. And then on the other side, we have a pressure gradient force, which is 10 to the minus 5, inserting what is here. And then we have Coriolis force is 10 to the minus 8. So here you can see that all these terms on the left-hand side can be neglected with respect to the horizontal pressure gradient force and the Coriolis force on the order of 3, 10 to the minus 3 is the good assumption of this thing. So that means that if we are dealing with a time scale, if we are dealing with time scale of 10 to the 7 seconds, 10 to the 7 seconds is 100 days, around 100 days, I think. If you are dealing with processes which have a spatial scale of 10 to the 6 meters, so it's 1,000 kilometers. 1,000 kilometers and 100 days, you can assume the Coriolis force. The Coriolis force, therefore, or the Coriolis, sorry, not the Coriolis force, the geostrophic equilibrium. So that means that the geostrophic balance applies to oceanic flow very strictly or pretty strictly if you are dealing with processes which are very slow processes which are changing on a time scale of 100 days and 1,000 kilometers. In practice, this balance applies to oceanic flow with horizontal dimensions larger than roughly than 50 kilometers, so it's even less than that, and times greater than a few days. So wherever we are dealing with processes which are changing on a time scale larger than about 50 kilometers, which is close to the 100 kilometers, and times greater than a few days, I think that, let me see, 1 day is 100,000 seconds, more or less. If we talk about yeah, yeah. So it's more or less this thing. So if we are talking about the processes which are large, which have a scales larger than 50 kilometers, and changing on a time scale of a few days, then in that case the geostrophic balance functions. So you can see that by these considerations, by this what we call the dimensional analysis, we we have obtained how good is the geostrophic assumption, and how good the geostrophic flow approximates what we really measure in the ocean. So, for example, if we do the measurements in the ocean and we do how do we get the something which is as close as possible to the to the geostrophic flow? Simply, if you do the measurements at a certain point, and do your measurements, or at a certain point, and do your measurements for times greater than a few days, greater than 10 days, than a month, to make sure, and you look at the processes which are larger than 50 kilometers, your measurements will be as close, very close to the geostrophic flow. Therefore, it might not be necessary to do the in situ measurements with the instruments. It might be enough if it were simple. It might be enough to measure the horizontal and vertical distribution of density and obtain the flow. A similar thing is if we are talking about the surface circulation. The surface circulation has a very good approximation for the geostrophic flow for the surface flow. Is a very good approximation, for example, if we look at the satellite data. Because why? Because the satellite data, as you remember when I mentioned before, that the coverage of the whole ocean with the sea level measurements in the order of 10 days. So in the order of 10 days, you obtain the entire structure of the sea level over the world ocean. Since we said that the geostrophic flow represents a very good approximation for the dimensions, horizontal dimensions larger than 50 kilometers and times greater than a few days, we are certainly within these time limits and space limits where the geostrophic assumption is valid. So that means that we can use with very good approximation the measurements, the sea surface current measurements obtained from satellite. This is why the satellite measurements are extremely important, not only for the distribution of the sea level, but it's also important for the measurements on the flow. Obviously, the situation complicates to a large extent if you want to go to and reconstruct what is happening in deeper layers, because of what I told you before, because of the horizontal pressure gradient due to the horizontal density distribution. And so we are not supposed to go below the sea surface in order from the satellite measurements. So we have to stay at the surface. So this is why the satellite measurements are good. They are good because they gives you the very high resolution, but at the surface, it doesn't give you any information on what is happening below. This is how and why we do have to okay. I don't want to do this thing here. Okay, so that's that's why I wanted to tell you these comments on geostrophic currents. And this is the comment on the surface geostrophic currents from altimetry. We will be coming back to altimetric surface geostrophic current measurements more than one situation. And we have explained under which conditions and what are the times and depth scale under which we have the hydrostatic equilibrium, and so that's this thing here is. With this, we will be finished the this part here. Here is again the Gulf Stream. Here is for example, this thing here, sea surface height in the Atlantic. These are obtained based on drifters. So what has been obtained? This thing, if you put into the ocean, you can do the opposite operation. You can measure the sea level, sea surface height distribution, and then obtain the flow. But you can do the opposite operation. You can measure the surface current with enough good resolution, and then reconstruct the sea surface. How do you do that? Again, from the geostrophic ocean. Here is these are the results of the surface height reconstructed from the surface current measurements. How do we get enough surface current measurements in order to obtain such a good reconstruction of the sea surface height? By drifters. What are the drifters? We'll be talking about drifters much more later on. For the moment, I will just tell you these are the instruments. What you throw into the sea, what they do then, they simply follow the currents, and you obtain every hour or every certain period of time, you obtain the position of these drifters. From the differences of position between the subsequent hours or subsequent times, you estimate the velocity. So each drifter, what you threw into the sea, gives you every hour the speed, the surface speed, and therefore, if you threw enough drifters into the ocean, you will be able to reconstruct the flow over the entire ocean. For example, here we have the example of the Antarctic of the Atlantic Ocean. And then you do the inverse operation. You start with the flow. You have on the left-hand side, you have FV Coriolis flow, Coriolis parameter, Coriolis force. On the right-hand side, you have the horizontal pressure gradient, or due to the sea level. So your noun in that case is horizontal pressure gradient due to the sea level slope. And on your left-hand side is a known velocity field. From the known velocity field, you calculate the sea surface height, sea surface pressure, sea surface height gradient, and then you obtain the sea surface height as it is here. You can see how this reconstruct or pick up very well the what we have seen from the altimetric data. Again, the Antarctic current, you get again here in these highs, subtropical highs, you have here the lows, and so forth. They are very, very similar what we have obtained. And this is the same thing, but in the Pacific. Again, this is obtained with the same way. You can see that these are the measurements in this paper is in 2003, and at that time there was already in the world ocean launched like 2,000 drifters all over the world ocean. Therefore, the resolution of the possibility to reconstruct the flow in the world ocean was rather rather well, and there was a rather strong horizontal resolution. Sea surface height in the Indian Ocean, the same thing, from the same database. And that's it. That's what I would like to tell you as far as the geostrophic flow is concerned. Now, if you have a few minutes of okay. Now I will try to find for you, if you, I will find for you another PowerPoint lecture. Okay, let me see. Okay, let's see. So now we will be talking about the let me see. Okay. Now I will talk to you about the vorticity in the ocean. About the vorticity in the ocean. And let me make the condividere lo schermo. Can you see it? Can you see it?
We don't see the slides, Professor.
You don't see. What do you see? You see me?
No, we see your folder.
Ah, you see out my folder. Okay, let's. Yes, but no. Okay, interrompi. No, let me tell you. Let me see the. Okay. Just a minute. So you see now this folder, right? Now you don't see it.
Now you're not sharing anything, Professor.
I'm not sharing. I don't want to share. Evidently, I don't want to share with you anything. Okay, let's. Okay, sorry. Let me find the right let me find the right that's it. Here it is. Can you see it? Good.
Yes.
Yes.
Okay. I will just start talking with about the. What are your background? For example, Michi Tevera, what is your background?
This is my room, Professor.
What?
It's my room.
No, what is your background at university?
I took applied physics and material science and engineering.
Okay, good. Thank you. And Aminat?
Physics, pure physics.
What physics?
Physics, pure physics.
Pure physics. Okay. Andrea?
I'm a geologist.
Oh, okay. Okay. So none of you are meteorologist or oceanographer. This is something what at least from the not from the formal, from the mathematical formality, but from the phenomenological point of view, it's something which is I hope new for you, so you don't you are not bored.
Yeah.
Okay. So we'll be talking about the vorticity in the ocean, and here is the vorticity. Is the planet? We have a planetary vorticity and relative vorticity. What is planetary vorticity? Since we are staying at the rotating system, we have the planetary vorticity, which is proportional to the angular vorticity of the Earth, or to the angular vorticity in a function where you stay at the Earth, and because it is function of sinus phi. Phi is the latitude where you are staying. So the planetary vorticity is this thing here. So is cycle in a cycles per day. On the other hand, you have the relative vorticity. So this planetary vorticity depends simply on where you stay at the rotating Earth. The relative vorticity, on the other hand, is the horizontal vorticity vector, which is associated only with the horizontal gradient of density of velocity. Okay. And we assume that the flow is two-dimensional. So this is so we have the planetary and relative vorticity, and then we have absolute vorticity, which is the sum of the planetary and relative vorticity. We'll be coming back to this vorticity in a number of situations, so that don't worry if you have some problems in this very beginning. And the equations for absolute velocity in a frictional ocean, in frictionless ocean, is this thing here. So you have the total derivative of theta plus f, which is theta is relative vorticity, f is planetary vorticity, and then is theta plus f multiplied by this is divergent term, the divergent term. So this, how we obtain this equation? Let me see. We can. I will come back to this thing later on. How we obtain from the formal point of view? How do we obtain this equation? But anyhow, this equation has been obtained from starting from the equations of motion, and this is why it says in frictionless ocean. In frictionless ocean means that on the other hand, on the right hand side of the equation, you don't have friction, you don't have anything. Horizontal pressure gradient doesn't impact the velocity. So we have only these two terms. So you have and this ddt is the absolute derivative, which consists of partial derivative and advection term. So you have, on one hand, the local variations of absolute vorticity, and then you have the advection of the vorticity. And let's see how is defined vorticity. Vorticity is defined as a vector, so that it has the right hand rule. Thumb up means positive vorticity. Positive vorticity means that you are going in this way. The thumb is showing up, and this is the positive vector of the vorticity, and negative is on the other side. This is one thing. The other thing is that sorry, let's go back. The other thing is that the vorticity, the relative vorticity, depends on the horizontal gradient, of velocity. So if you go here, and on one hand, if the vector, your parcel is moving along the circle this way, it will have the positive vorticity. But this positive vorticity you will obtain also if you have the currents which are changing in this direction, in that way. So you have this thing here. You have the weakening. You have the weakening of the current going from south to north. So there is the horizontal gradient of currents. So the two processes are responsible for the vorticity. One is the horizontal shear, which is this thing here, the changes of the velocity perpendicular to the direction of the current. And the other one is simply circular motion of the particles. And the vice versa, negative vorticity, which is this way here, you have the current increasing from south to north, or you have the particle moving along the circle in the direction, in the clockwise direction. So these are the two ways how the vorticity can manifest. And so that's so the potential vorticity. It's like an angular momentum, but applied to a fluid instead of a solid. Angular momentum. So you have the potential vorticity, which is a planetary vorticity plus relative vorticity, divided by column height. So the potential vorticity is absolute vorticity divided by the height of the water column, by the depth of the water. Potential vorticity then has three parts, okay? Three parts. One is relative vorticity due to the fluid circulation, we have seen before. Planetary vorticity due to the Earth rotation, which depends on local latitude when considering local vertical column. Then we have finally the third term, which is a stretching. So you have a squeezing or stretching of the water column, which is due to the fluid water column stretching or shrinking. The two vorticities, 1 and 2, and together to make the total vorticity. The stretching height of the water column is in the denominator, since making a column taller makes it spin faster and vice versa. It's like a ballet dancer, and when she dances this way, when he stretches, when he shrinks the hands, and starts to turning faster. So we define the potential vorticity. This is a very, very important parameter in the ocean, because it will give you also the idea how the water column is moving. If we divide the previous equation, if we divide the previous equation by h, we obtain this thing here, okay? This is the equation of conservation of potential vorticity. Conservation of potential vorticity simply says that the potential vorticity is conserved along the particle, along where the particle or the water column is moving. So if you follow the water column which is moving, it has the potential vorticity has to be conserved. What that means? That means that zeta plus f divided by h has to be constant. So if we increase h, the zeta plus half has to increase as well. Or if we decrease this thing, we have to decrease as well zeta plus f. So how do we do that? We do in various things. For example, the h is something which is the outside conditions. If you go to the shallower part of the water column, we somehow have to decrease this thing here. How would we decrease this thing? Or the water particle will be moving, turning slower, or we can lower this thing here. How do we lower this thing? We simply go toward the equator, because toward the equator, F is lower than toward the poles. So this kind of this law, conservation of potential vorticity, determines how the water particle will be moving in order to preserve the potential vorticity. And relative vorticity, which is this thing here, is usually smaller than the planetary vorticity, because dv dx, dv dy, dv dx, or du dy are usually smaller, and they are on the order of because if you have the speed on the order of 10 centimeters per second, which is typical speed in the ocean. So if you divide this by typical scale in the ocean, which is 100 kilometers, 0.1 divided by 10 to the 5 is 10 to the minus 6. And 10 to the minus 6 is a typical value of the relative vorticity. The absolute vorticity, as we have seen before, is 10 to the minus 4. So the relative vorticity is 2 orders of magnitude, typically 2 orders of magnitude smaller than the planetary vorticity. However, there are some limited areas in the ocean where the relative vorticity in the open ocean is found at the edge is larger, or is at the same order of magnitude as the planetary vorticity. And this is typically at the edge of the western boundary current, where we have the horizontal velocity gradient on the order of 1 meter per second to 100 kilometers. So we are an order of magnitude larger relative vorticity, and this is on the order of. So we have to take into consideration this. We cannot neglect this with respect to that one. Thus, one can assume in the first approximation, except in these very special areas along in the ocean, that in the first approximation, the water particle should move along the lines F over H, because only along the line F over H, constant, d dt is equal to 0. So we can, in the first approximation, we can assume that in the ocean, that the water column, the water particle, is moving along the F over H, along the lines F over H constant. This is already one great information what we get. So that means that we plot the lines, the isolines F over H, we obtain the lines of along which the lines at which the velocity is tangential. That's a very, very important information on the flow. Obviously, we know that if you go to the boundary, western boundary current, that this is not satisfied, and then there are larger larger departures from this equation. But in the first approximation, this is a very good thing. Let's see. With this, I would finish, and we will continue next time. So you will have more time to think about this. Potential vorticity balances. Here we have examples with each part of two terms. Okay, this is let's see the term zeta, the term where plus zeta over h is constant. If with the zeta, if the relative vorticity is changing, and so we have here relative vorticity is 0, and here is relative vorticity 0, but here the water column is here squeezed with respect to this one. So here the relative vorticity is larger than here. The particle practically is moving faster, and if the water column is stretched. So in order to maintain this zeta, in order to maintain this constant, we have to make a decrease this f, because this is increased. If h is constant, if h is constant, h, the depth of the ocean, is constant, then we have to decrease this thing here. So how do we decrease this thing? We decrease f by moving the water column towards south. So in the same amount as there is an increase of the relative vorticity, the same amount the planetary vorticity has increased, and this makes this q is conserved unless we don't have the changes of depth. And we will talk about this later, because that's the potential vorticity balance for the large scale general circulation, and we will see later on how it looks like. And here is one more example of this where how the depth in fact impacts the movement of the particle. We said before that the particle or the water column is moving in the ocean by keeping the f over h constant. So what is happening if so the particle is starting from here, going this way. Suddenly it meets the part of the ocean which is shallower. So h becomes smaller, and in order to keep f over h constant, the f has to become smaller. Therefore, the water particle or the water column has to move, leaving this bump at the bottom, leaving this bump at its left, going southward. So the only way one flow, barotropic flow, barotropic means that it's homogeneous from the surface to the bottom, can bypass a shallower part of the ocean in order to keep the constant, the conserved potential vorticity, is to leave the bump in the bottom on its left. Or in other words, obviously it turns equatorward on the northern hemisphere. So if you have a subsea ridge, it turns equatorward and then goes back and passes the ridge. And this is how it conserves potential vorticity, because the h becomes smaller, and then in proportionally f the Coriolis parameter becomes smaller as well. Well, let's see. Let's talk about this this later about this next lecture. So I would suggest to stop here. I will try to share my within this week. I will share my PowerPoint with you, so that you can look if you have time. With this beautiful weather, I don't know whether you will have time. And so we'll be seeing each other next Wednesday at the same time. Okay, have a good time. Ciao.
Yeah, bye.
Ciao.
Bye.
Ciao.
Thank you.
Thank you so much. Have a nice day.
Thank you. Bye bye.